Luckily, robots don't drink beers and are more responsible than us. Nevertheless, they suffer the same issue as we humans do in terms of localization and position tracking, especially during extended movements. But first of all, what does it mean for a robot to be localized? Robot localization denotes the robot's ability to establish its own pose and orientation within the frame of reference. This definition shows that the localization problem involves two actors, two components. On one side, there are the reference frame, and on the other side, there is the position and the orientation of the robot, which we can define as the robot's pose. Reference frames are amazing, and we, as humans, continuously make use of them. We have even identified a global reference frame to uniquely indicate our position on Earth through geographical coordinates of latitude and longitude. But we are also very good at creating new, original, and weird reference frames, sometimes perhaps even too much. In short, a reference frame is a point against which we express our position, namely the origin, so the point 0, the point against which we express the position on the object in space. Regarding the geographical coordinates, the reference frame we use, so the point that we consider as the origin, is given by the intersection of the equator and the Greenwich meridian. This is the point of latitude 0 and longitude 0, somewhere in the Atlantic Ocean. After clarifying the concept of reference frames, let's move on to the second actor that we mentioned in the definition of the localization, which is the position and the orientation of the robot, indicating the overall pose of an object in the world. When we use reference frames, such as the geographical coordinates, we express our pose in terms of latitude and longitude, where the latitude is the angular distance of a point from the equator and longitude is the angular distance of a point from the Greenwich meridian. We can group these coordinates into a single vector called pose. Now, in the specific case of a self-driving robot that moves on a flat surface, we can define a two-dimensional reference frame. Simply put, we can fix an origin, so a point with coordinates 0 and 0, against which we express the pose of the robot, namely its position and orientation. Once the reference frame is fixed and the pose of the robot is defined, the localization problem simply becomes the one of measuring the coordinates of the robot, so the quantities x, y, and the orientation angle theta that is relative to the reference frame that we have fixed. Similarly, if we consider a different robot, let's say a drone that is capable of moving in the three-dimensional space, its pose will be expressed relative to a three-dimensional reference frame and therefore in terms of coordinate x, y, and z, and the three orientation angles.